Okay, good evening everyone. This is Ryan at the National Weather Service in Norman again. We had a few people log in additionally. It looks like quite a few people on this evening. You can hear the webinar through your computer speaker, so there's no reason to call in on the telephone, and you won't need a microphone for this one. And like I said, I'm Ryan Barnes, and I have Vivek Mahali here with me as well, and Mark Austin. If you're going to tweet tonight, you can use the hashtag #OUNSpot. And some frequently asked questions real quick. Is the webinar being recorded? Oh, no. Will the slides be available? Yes. And we'll get a link to those slides sent out to you. And yes, you will get a certificate that's going to be emailed as well after this is over in the next few days. So the email that you used to register for this, that's what we'll use to email you the certificates. Okay, so since you can't use your microphone, if you would like to ask a question, this is showing you how to do so in your little GUI box up there on the top. And we'll answer as many as we can. Like I said, we have 3 people here. I'm doing the presentation right now. We're going to switch off through the evening. But we have 2 people answering, Vivek right now and Mark are answering questions, and we'll get to those as fast as we can. Okay, so right now, if you would, I know there's people who are having these in the office or in conference rooms. How many people are attending the training right now with you? Whether it's you by yourself or a few of you, if you would do that right now and also put where you're located, county and state, or even country if you're out of the United States. Okay, so we'll give you a few minutes to do that. All right, so for the advanced severe weather topics tonight, here's what we're going to talk about. First, we'll look at the actual severe weather ingredients needed for supercells, tools for accessing those ingredients, and then we'll take a short break, and we'll look at the storm structure after that and evolution, and then positioning when you're spotting and how to make an effective report. All right, so briefly, let's talk about some severe weather meteorology. So here's a look at a composite chart. This is done by Maddox and Crisp in 1999, and this is actually for March 1948. It's just showing you all the ingredients basically that you need for severe weather. There's quite a few ingredients. This map is very busy, but there's 4 basic things, 4 things that you need to remember to have severe thunderstorms. And those ingredients first include moisture, and instability, lift, and wind shear. So to look at the top left here, ingredients for a supercell, moisture, and in the southern plains, our moisture source for low-level moisture is the Gulf of Mexico. All right, and then in the top right, you can see instability, and those are what we call forecasts, or those are what we call sounding profiles. And then you'll need some form of lift, and that image there is showing convergence at the surface, forcing the air upward. There's different forms of lift that can be used to lift the air. And then finally, to get rotating updrafts or persistent rotating updrafts, the definition of a supercell, you need wind shear. So we'll talk a little bit about that as well. Okay, so where can you monitor this data? Well, the best place to monitor a lot of this stuff is the Storm Prediction Center site. And you can see the address, so it's spc.noaa.gov. There's tons of information on this page, but there's 2 areas, 2 tabs basically that are pretty important. So the watches, the mesoscale discussions, the outlooks, and the fire outlooks are all right there on the top right. And then to the left of that in the blue row, here's where you have your meso analysis, and then you can look at the storm reports, again, the mesoscale discussions and the watches. But if we click on the forecast tool, so if we go back up here, you can see at the very top of this page there's a forecast tools link as well. If we click on that forecast tools link, you'll get a page similar to this one. So there's lots of different things on this page, but there are three important things with regards to severe weather. The first is upper air maps. So you can look at all the different levels of the atmosphere, and this is from the balloon sounding data. So these are from the radio zone data, and that's going to, so it's going to be at 12Z or 0Z. And so you can look at all the different levels, 250 millibars, 500 millibars, 700 millibars, and so on and so forth. And it's just an analysis of those maps. So you can look at the upper jets, the low-level jets, and so on and so forth. And then the next thing you can look at are the observed soundings from the balloons. So here in Norman, we send balloons up twice a day, every day. And so that gives you a vertical profile of the actual profile of the atmosphere. And we'll talk about a little bit about Cape and Sin a little bit later on. And then finally, at the bottom, the mesoanalysis graphics, and there's lots of different parameters that you can look at with regards to severe weather on this mesoanalysis graphics page. And you can see those little boxes on the map there, it's sectorized, so you can look at different regions. Okay, so the first ingredient that we talked about, moisture. And like I already mentioned, our primary source here in the southern plains is going to be the Gulf of Mexico. And when we're looking at dew points around 50 to 55 degrees for supercells, and obviously that varies depending on the environment, but in the case for tornadic supercells, we want much higher dew points than that. Okay, so here's a look at a dew point temperature map from May 10th of 2010. You can see it's very, very moist across all of Oklahoma in this image. So these are the dew point temperatures. And you can see, if you look at the little blue lines or the little blue barbs, those are our winds, and they're the direction from. So when we're in meteorology, when we're looking at wind barbs, it's the direction of which the wind is coming from. So you can see the winds are coming from the south across central Oklahoma and the south-southeast. As you shift to the east and southeast, the winds are out of the southeast and even east and extreme southeast Oklahoma. So that's how we're getting our low-level moisture there. Okay, so if you're looking at a sounding, and if you go back before and you go to that Storm Prediction Center page, if you go to a sounding, the dew point temperature is analyzed all the way up through the atmosphere. So if we're looking at this, we're going up through the atmosphere, starting at 1,000 that's 1,000 millibars of the surface there. You can, if you look at the bottom left-hand corner, you can see SFC. That's the surface at 357 meters, and then we keep going all the way up. But this green line here is the dew point temperature. Okay, so moisture is very key in tornado genesis. So you need abundant low-level moisture. And what that does is it results in high instability in the low levels of the atmosphere. And when you get that high instability, it results in strong, persistent updrafts. Okay, so in the lowest part of the atmosphere, you have very persistent and strong updrafts. And here in the southern plains, obviously we want southerly to southeasterly winds to transport that moisture from the Gulf of Mexico. And then we want low dew point depressions, or the difference between the temperature and dew point, for lower cloud bases and tornado formation. Okay, so or the LCL, lifted condensation levels. Okay, so here's a look at a surface observation map again, and the red numbers on here are the temperatures, and then the number below that, either orange or green, are the dew points. So you can see right there, Oklahoma City, in the center of in Oklahoma, obviously, it's 90 over 68. So the temperature is 90, the dew point is 68. It's very moist. It's very unstable. The Cape is around 3,300 joules per kilogram. And again, we'll discuss Cape here in a second. And several tornadoes were reported on this day on May 9th. So, but the key thing to remember here is this is just one key ingredient that you need for tornadoes to occur. There's several different places, and you might already have somewhere you go to monitor moisture. But here's a few examples. You can head over to the Mesonet, mesonet.org. and you can monitor the dew points there. That's that upper left-hand map. And then on the right, this is a surface analysis from UCAR. So this is rap.ucar.edu/weather. And then you can click on surface there when you get there and look at the analyzed surface map. In the bottom left, that's from the Storm Prediction Center. Already mentioned that earlier. And the same thing bottom right, that's your sounding profile of the atmosphere. Okay, we talked about moisture. Now the next ingredient that we need for supercells or severe weather is instability. And that generally means that we want colder, drier air above moist, warmer air near the surface, and that creates instability. Okay, so let's go through actual sounding here, and you'll see the colors over here on the left side of the slide change according to the colors of the sounding on the right. So for the red, it's the temperature of the environment as the balloon climbs up. So if we're looking at the red line, it's the temperature of the actual environment as this balloon climbs up through the atmosphere. On the right side of the image, it's hotter. On the left side, we're colder. Okay? Okay, so if we take this bubble, just to kind of imagine like this bubble of air as it rises, and when it gets to a certain point, it becomes saturated, and it cools at a different rate now. So that's the yellow line on the sounding that we're seeing. So that's actually taking like some ball of or a bubble of air and forcing it upward. What would happen? Again, the green line is the dew point of the environment, and then the orange shaded area is what we call convective available potential energy, or CAPE. Okay, so on the left-hand side there, the left-hand sounding, we have a lot of CAPE, a lot of fat CAPE, as what we say. And then on the right side of the right sounding is we have tall, skinny CAPE. Okay, so let's look at stable versus unstable. On the left, we have cool air underneath warm air. In this case, will the balloon rise? So cold air is more dense or heavier than warm air, so it's not going to rise. So even if it gets forced up a little bit, once it gets warmer, it's going to drop back down. So it can't rise. On the other hand, on the right side, we have warm air underneath cooler air. So if we give this a little nudge upward and we start to rise, it will continue to rise because it's warmer than the environment, and that is unstable. So on the right, we say it's unstable, or we have positive instability. Okay, what happens though when you have what you've heard many times, I'm sure you've heard before, is the cap, or inhibition. So you have this warmer layer above the warm below, and you can't force your way through it unless you get something really strong to nudge it through that cap. So when we talk about the cap or convective inhibition, this is what we're talking about, is that warm layer above the warm surface layer. And here's what that would look like on a sounding. So this is often referred to as CIN, C-I-N, convective inhibition. So that blue shaded area now on the sounding is our actual CIN, and that's how you calculate CIN. And you can see again the orange shaded area that we have highlighted is the CAPE. So the areas of these two, that's how we calculate CAPE and CIN. We find the areas. Okay, I briefly mentioned this before. So on the left we have a high CAPE and we have a fat CAPE basically. So in other words, the temperature decreases much more quickly on the left side here. There's that black line. On the right side, the temperature doesn't decrease as quickly with height. So we have low CAPE or skinny CAPE. Okay, so this determines basically the amount of thunderstorms that are possible, or the potential in that area. Okay, there's lots of different places you can monitor the instability. Again, if you go to the SBC page and you click on the meso-analysis with the sectors, and if you click on your sector and you click on the thermodynamics tab, there's lots of different parameters that you can take a look at. So when we look at CAPE, ideal for instability analysis, we often use the mixed layer CAPE for a better analysis of the actual environment and what's going on. Lifted index, the more negative, the more unstable, basically. That's how you look at lifted index. And then mid-level lapse rates for hail potential. So you want to look for 7.5 to 8 degrees Celsius per kilometer. That's indicative for some larger hail threats. So basically lapse rates means how fast is the environmental temperature cooling with height. So the faster it cools with height, then the higher the lapse rates, obviously. The LCL heights for tornado potential, and then you can also monitor the short-term changes in these fields. So this next thing just shows you the thermodynamics tab zoomed in as all these different parameters that you can look at from the SPC page. Okay, so now you may or may not known this before, but now if you're looking in National Weather Service discussions, including mesoscale discussions from the Storm Prediction Center, you'll see these words destabilize and negligible sin, modest instability. Now you'll have an idea of what those mean. So in this case, there was very little sin or cap where the surface temperatures exceeded 83 degrees Fahrenheit. Okay, next ingredient that we need for supercells, obviously we need something to lift the air up. Okay, we need something to nudge it upward. And these include any sort of boundaries like cold fronts or warm fronts, dry lines, and even outflow excel from thunderstorms can generate lift. And also not mentioned here are upper level forms of lift in the atmosphere as well. But usually you need something near the surface. Okay, so just a brief look at warm fronts and cold fronts. Warm fronts, you get lift with them, but it's a gradual lift. You can see in this graphic, it's a gentle lift. With cold fronts, it's much sharper. So you get a cold air mass, and the air is abruptly lifted, so it's very drastic. So you'll get those real strong updrafts that may start to develop along a cold front. And a lot of times with especially strong cold fronts is when you can get linear storms develop, such as squall lines. Okay, so what happens near fronts or boundaries is the air converges at the surface and it's forced upward. So that's where you might see convergence in a discussion. That's what's going on. So we're talking about convergence along the dry line or a cold front. This is what's happening. So you're converging the air near the surface and it's rising. And here's an example of a very sharp dry line here. And it's easy to tell from the graphic where the dry line is, the yellow line denoted here. And we have winds from the southeast, east of the dry line, and then west, southwest, west of the dry line. So that's the convergence. Excuse me. Now, if we look at the radar associated with this boundary, you can see the storms developing in the warm, moist sector, as we say, and then exploding and staying east of the boundary as they move east, northeast. Okay, here's an example of an outflow boundary, and you can see the cluster of storms in the middle. This is just showing you the cool air from the thunderstorm spreading outward, and then you can see on radar the actual outflow boundary extending away from these storms. Well, it's actually a density boundary, and then oftentimes, especially if the flow is exactly pretty much 180 degrees opposite of that, then you can get strong updrafts to develop along the boundary and then lift right behind it. So you could see additional development or additional storms developing along those boundaries. Okay, here's another example where you can monitor any surface condition. If you want to look at dry lines or cold fronts, you have the winds and the dew points and the temperatures, the wind gusts. So these are what the arrows are pointing at. In the box that's highlighted, it'll show you everything that you need to know. So it's basically the key for the surface map, and that's always on there. So if you head over to mesonet.org and you look at current weather conditions, if you click on current weather conditions, you'll get this map and you can check out all the goodies. Again, back to the Storm Prediction Center page. Same thing here. You can monitor the surface observations here as well. And you can click on the basic surface and see all the options that you have. Okay, we talked about moisture. We talked about lift, instability. Last thing we need for supercells is something to spin the air. In this case, wind shear. So we're talking about increasing wind speeds or direction with height. And for supercells, you need deep wind shear. So a lot of times you'll see 0 to 6 kilometer deep layer shear or effective shear, bulk shear. That's what we're talking about here. So we're looking at basically the speed changing with height and the direction changing with height. Now for tornadoes, you also need to have low level wind shear. So here's an example on the far left, and we're going up with height. On the far left, we just have the arrows increasing, so there's no change in direction, so we have speed shear. In the middle, there's no change in the arrow's length, so we're changing the direction though, so we have directional shear. But both is very substantial, so if you have both of those combined, and which is the last line arrow here, we're changing direction and increasing speed with height. So here's a look at actual what's called a hodograph. So if you look at some sounding pages, wherever you may go, these are hodographs. So it's basically depicting each arrow is starting at the cross. They're right in the center. And for instance, so the first arrow that you see there pointing to the SFC, or the surface, you can correlate that with the wind barb on the right there. So we have a wind barb coming from the southeast, and that correlates to that arrow on the hodograph pointing. So that's our first point. Now as we go up, we start at the same point and we keep drawing these arrows out as we go up. So each different number, 1, 2, 3, corresponds to these numbers over here on the right, or the profile from the sounding. And this is how we get our hodograph. So this is speed. We get this big looping arc that starts on the left and arcs clockwise. Okay, that's a curved hodograph. So we have directional and speed shear, especially near the lowest 4 kilometers of the atmosphere. And this is called, when we look at this, this is what we're saying as helicity. Okay, it's basically a measurement of spin in the atmosphere. Okay, so how do we find shear? Do the winds change in speed and direction as you move from the bottom of the sounding up to around 500 millibars, or the mid to upper levels of the atmosphere? Okay, so looking at this sounding here, you can see near the surface we have southeast winds, and as we go up, we have west-southwest winds increasing with speed. Very strong west-southwest winds there. So yes, we have the deep shear there from the surface up to about 500 millibars. Okay, so shear for the updraft potential rotation. Okay, do the winds change in the first half mile as you move up from the surface? So again, here we're looking near the surface. We have about, same thing, southeast winds, and as we go up, we increase in speed dramatically as well near the first half mile. So that's about 40 knots there at 800 millibars. So that's the low-level shear that we need for strong updraft rotation or tornadic supercells. So here's another example of wind shear, maybe what it would look like as we increase and turn the winds with height, and we start to spin basically this tube of air horizontally. Okay, so right now we have this rotating tube of air that's horizontal to the surface. So you're thinking to yourself, well, where's the rotation come from for storms if it's just rotating this way, horizontal, or basically parallel to the ground? Well, what happens is the thunderstorm develops an updraft, and it tilts this tube into a vertical or quasi-vertical column of air. And now we're translating that into vertical rotation as this updraft comes along. So if you add the updraft, now we have rotation in the vertical, and that is the origin of rotation for potential tornadoes, or the origin of rotation for supercells or mesocyclones. Okay, so we define a supercell as having a persistent rotating updraft, or a mesocyclone, and the source of the rotation, as I mentioned, comes from the meso, or the wind shear. Okay, so to increase the likelihood of a tornado, we need to increase the low-level shear or helicity in the atmosphere. Okay, this increases the potential to develop a persistent rotating updraft that's strong. And this helicity increases along boundaries such as outflow boundaries or warm fronts. Tornado genesis is more likely if a supercell travels parallel along the boundary. Okay, so warm fronts especially. So you can increase the shear or helicity along a warm front. Okay, here's another analysis. This is at 850 millibars. And you can see the red arrow there across central and east central northeast Oklahoma. This is depicting the strongest winds at 850 millibars, so around 50 plus knots there. This is the low-level jet. So these are winds just above the surface. So as we increase, a few thousand feet above the surface, if we have weaker surface winds, you increase the low-level shear or helicity. That's why oftentimes you'll hear the low-level jet discussed so much. During the evening hours when the low-level jet starts to increase, you start to increase the low-level helicity, and therefore, if you have the supercells in place already, if that low-level shear or helicity starts to increase, then you increase the chance of tornadoes as well. Again, you can monitor the wind shear. It's another tab at the SPC mesanalysis page. And you can see some of the things that I talked about before. This over on the right-hand side, the storm relative helicity effective, and then the bulk shear effective. So the very first link on that in the gray area, and then when you can see the horizontal line, the first horizontal line, the first storm relative helicity effective. Those are the two important ones right there. Okay, so that includes my section. If you have any questions, continue to ask them. We're going to take just a very, very short break. Don't get up and leave, but we're going to take a very short break to change seats here so Vivek can get in here and talk about tomorrow's setup. So bear with us just for a couple minutes, and we'll be right back. Thanks a lot.
All right, well, as Ryan said, we're going to be talking about our setup here in Oklahoma tomorrow, and kind of using the stuff Ryan talked about in his section. First of all, here's sort of our forecast for tomorrow. So again, Wednesday, there's currently a slight risk of severe weather, including the Oklahoma City Metro, as well as an enhanced risk, including Ponca City, Enid, and Stillwater. And where storms do develop, they have the potential to produce large hail, damaging winds, and possibly tornadoes. The tornado potential is relatively low, but enough to warrant attention. Golf ball to tennis ball size hail and 70 to 80 mile per hour winds will also be possible with these storms. So let's take a look at the parameters of why we're expecting severe weather and why the greatest risk of severe weather is across north central Oklahoma near the Kansas-Oklahoma border. So I'm going to take you over to the College of DuPage website and take a look at some of the parameters that Ryan talked about in his section. First of all, this is the forecast dew points valid tomorrow afternoon. This is about 4 o'clock tomorrow afternoon from the NAM computer model. This is just a numerical model that is used to help us forecast the weather. And you can see we have very good dew points, very high moisture. Dew points are in the 60s, low to mid 60s across Oklahoma and Kansas. We also have a cold front across Kansas. You can see the boundary up in here from where my mouse pointer is. We also have a dry line centered to the west in western Oklahoma going into Kansas. So we do have moisture, very good moisture there. Dew points in the 60s. And Ryan talked about lift. Well, we have a dry line and we have a frontal boundary in this area here. So there's going to be convergence of air here. We have southeasterly winds coming in this direction, south to southeasterly winds. We have the northerly winds back behind the boundary, and we have southwesterly winds behind the dry line. And that all sort of converges right here in south central Kansas, just north of the border. So there's your sort of source of convergence or source of lift for tomorrow afternoon, and also the moisture as well. Now Ryan also talked about instability. So here is the CAPE, forecast CAPE for tomorrow afternoon, and you can see we have quite a bit of instability across northern Oklahoma and southern Kansas near that source of lift. In the blue we have the convective inhibition. You can see the convective inhibition increases the farther south you go. So the least inhibition is actually located pretty close to the border with the highest instability. So we have the lift, and we also have the instability located right near the border. And because the inhibition increases as you head farther south, for example, here we're going to advance to 0Z or 7 o'clock tomorrow evening. You can see the inhibition is still present farther south, while we're basically inhibition free across north central Oklahoma and southern Kansas. And that's part of the reason why there's higher confidence that we're going to see severe weather farther north into southern Kansas and northern Oklahoma. The farther south you go, there's more convective inhibition, so the risk is a little less. Now there could still be storms that can develop down here, but we have higher confidence that storms will develop farther north near the border, and that's where we have the highest risk or the enhanced risk of severe weather. So there's the moisture, the instability, and the convergence. But what about wind shear? We'll start out with the winds aloft. These are winds at about 500 millibars, so about midway up the atmosphere. And you see we have sort of southwesterly flow aloft, winds coming from the southwest to the northeast. So again, that's at 500 millibars. Let's go down a little bit closer to the surface and look at 850 millibars. This is about a mile above the surface or so. And we see winds here are generally from the south. So you see the winds are south going to southwesterly. So we do have directional shear going on in the mid-levels, low to mid-levels. If we go a little bit lower, let's go to 925. This is a lot closer to the surface. Winds are again generally from the south. And if we go to the surface, winds at the surface are also from the south. So just near the lowest, say 1 kilometer, there isn't a whole lot of directional shear. More of the directional shear is in the mid-levels. Because of that, the tornado potential is a little bit more limited. It's a low potential for tornadoes, relatively speaking. Now up near the Kansas border, where we have that triple point setting up with the cold front and dry line, you may get some localized backing or localized areas where the winds may become more easterly, and that would enhance the wind shear closer to the Kansas border. That's why there's a slightly better chance of maybe an isolated tornado close the farther north you go, and especially as you go into southern Kansas, the risk is a little bit greater because we have more enhanced low-level shear near that boundary. So again, if reiterating again, here we have the surface winds. They're from the south. If you go just a little bit off the surface, again, they're still generally in the same direction from the south, southeast, generally due south. And you can see there is not much in the way of directional shear. But if you go to the mid-levels, we have southwesterly flow aloft. So now we start seeing that directional shear, and that directional shear is more in the mid-levels where we do expect mesocyclones, mid-level circulations to develop. And because we have such high instability, again, if you go back to the mixed layer cape, again, we're seeing instability 4,000 or 5,000 joules, and the instability, joules per kilogram, excuse me, the instability is proportional to the updraft strength. So you have the stronger updraft, you have the potential for larger hail because of that. So that's something else to consider. So yes, you could easily see golf ball to easily tennis ball size hail with any storms that develop tomorrow because of the large amount of cape or instability in the atmosphere. But if you look at the helicity, again, the low-level helicity is not incredibly impressive because that low-level shear is not the greatest, and that is why the tornado potential right now is not extremely high. You can see the helicity does get a little bit higher right near the boundary, southern Kansas. Again, sometimes you do get localized enhanced shear right near boundaries and right near triple points. So that's sort of an overview of why we're going to see the potential for severe weather tomorrow and why the highest risk is across north central Oklahoma and southern Kansas. Again, let me reiterate, here's our graphic for tomorrow. Again, the enhanced risk is across northern Oklahoma, including areas such as Stillwater, Enid, and Ponca City. Inhibition is a little bit greater the farther south you go, but isolated storms could still develop even as far south as Oklahoma City and Lawton. It's less likely, but it could still happen. And if they do develop, the potential for golf ball to tennis ball size hail is there, and 70 to 80 mile per hour winds. All right, with that, we will go ahead and take about a 10-minute break. And Mark will come back and he will discuss a little bit more about storm morphology and storm structure and tornado genesis and tornado structure. And if you have any questions, you can go ahead and type them in. And again, we may not be able to get to all the questions. Yeah, we're about 7 to 8 minutes away. We are still on break, so if you aren't hearing any, yeah, we'll start about 7:20 Central Daylight Time. So again, if you are wondering why the audio went dead, we went ahead and we went ahead and shut the mic down, but we will be back in about 7 to 8 minutes. So don't worry if you can't hear anything right now. Okay.
All right, everybody. We are going to get started here again. This is Mark. I'm not quite as articulate as my coworkers here, Vivek and Ryan, but I will try my best. And we're going to get into some kind of nitty-gritty details here on storm structure and evolution. But first, I did want to address a very common question we're getting. It has to deal with the certificates for this training. And we will be sending a certificate out probably within the next couple of days. There will also be a link to the materials from this webinar. So if you want to go back and look at some of the slides or reference some of the links there, you can do that. If you have multiple people viewing this, we are not putting any names on certificates. So, if you want to print out several for the people that are attending with you, you can do that. But we do promise you'll get a certificate, and it'll probably come certainly by the end of the week. So if you're having trouble with that, if you haven't gotten it for some reason, sometimes we have a couple people fall through the cracks. Just get in touch with us. We'll make sure you get one, all right? All right, so we're going to move on now into some of the more interesting stuff here. We're going to spend a little bit of time talking about storm structure. And for this specific training, we're going to focus primarily on supercell storms. That's not to say that you can't have severe weather with other types of storms. Some of the other kinds that we have are pulse thunderstorms and multi-cell thunderstorms. But we're going to be spending the majority of our time here on supercells because those tend to produce the most significant severe weather. All right. So before we get into the nitty-gritty here, there are three main types of supercells. We have low precipitation or LP supercells. Those tend to be very picturesque, very beautiful storms. They kind of look like a barber pole. You can see in the image there at bottom left, and tend to be less likely to produce tornadoes. A lot of times the cloud bases with these are quite high. And then we move toward the classic supercells. These tend to be the ones that produce a lot more tornadoes, but also, of course, have the accompanying large hail and damaging wind threat. Finally, when we get toward the HP supercells, there's a reason why we say these are typically the most dangerous. And part of the reason for that is they do tend to produce tornadoes, but a lot of times they're not visible because they're completely wrapped in rain. And we'll look at a couple examples of that here shortly. So just remember LP, classic, and HP. We don't have a nice acronym for the classic supercells, but those are the kind that certainly produce the more widespread outbreaks. So let's take a look here. All right, so just the general anatomy of a supercell. Some of you may have looked off in the distance one day in the spring and seen something that looked kind of like this. Generally, it's not going to be quite this clear, obviously. This is, again, a schematic. So you basically have this large kind of cauliflower-looking what we call updraft, thunderstorm updraft, and that eventually will get tall enough that it hits what we call the equilibrium level, is where the tropopause is, and that's where the anvil forms. Now, if the updraft is strong enough, and it often is on the big severe weather days, you will have what's called an overshooting top that will punch through that anvil. And that's a sign that you have an extremely strong updraft because it's basically pushing, the momentum is so strong it's pushing all the way through that stable layer. Now, the equilibrium level, the tropopause, are not the same as the cap. Okay, the cap is much lower. It's usually around 850 millibars or so. So that's not the same thing. If you see a storm that is anviled out, it has definitely broken the cap. I can guarantee you that. So some other features here we're looking at. So obviously, aside from the tornado and the wall cloud, we've got these arrows that kind of spiral up with the updraft. That just indicates it's rotating. So we're looking at a supercell. Again, a supercell is a rotating thunderstorm. That's the general definition. We're going to kind of just go through this bit by bit here, so we don't want to focus too much on this, just a general picture. Here's an overhead view of kind of the same thing. And the color shading in the background is meant to be a simulated radar reflectivity of a classic supercell. Okay, so you've got this large area of very high reflectivity that kind of comes around with what we call a hook echo on the southwest side of the storm. Now, the southwest side of the storm is going to be the place you want to watch for tornadoes in most cases, especially if it's a cyclonic, right-moving supercell, a dominant supercell, within a very favorable tornadic environment. That's where you're most likely going to see the tornado development. That's not to say that in a pulse storm or multi-cell storm you can't get some little boundary interaction that can produce a tornado, but again, we're talking about supercells here. So we've got these two features here, the forward flank downdraft, the rear flank downdraft. We're going to go into both of those in more detail, and of course you have the updraft region there that's right on top of that hook feature. And you might notice some other terms here that we're going to touch on, the flanking line being one of those. Okay, so again, the supercell updraft. The picture on the right here obviously looks very similar to the schematic I showed you just a moment ago. You've got a very pronounced updraft, very crisp looking cauliflower or popcorn type clouds that rise up into this large flat anvil, and you even have an overshooting top here. So it's very likely the storm in this picture was a severe thunderstorm. You sometimes even develop mammatus clouds on the underside of the anvil. So those can be pretty spectacular at times. And the theory on the development of mammatus clouds is still pretty widely debated, so I'm not really going to go into how those form, but they certainly sometimes can indicate severe thunderstorms. All right, so what about the updraft itself? This is kind of getting more toward what we call a mesocyclone, but I'm going to go ahead and mention the striations or the striated features you sometimes see, if you're close enough to see them anyway, what the cloud base is going to look like. And those striations usually mean there's strong mid-level rotation. Sometimes you can see that descending toward the low levels as well if it's a tornadic thunderstorm. But usually if you've got strong mid-level rotation as you do in these two animations, you can pretty much bet you're going to have some very large hail, probably some damaging winds, and possibly even some tornado potential with the thunderstorm. All right, so another feature that we mentioned in the schematic was a flanking line. A flanking line is instrumental because it supplies a continuous source of updraft to the parent thunderstorm. If we just had one updraft go up and it was spinning like crazy, okay, that may favor severe weather for a short time, but if there's not a continuous feed of energy, of updraft to that parent storm, it's going to fizzle. So you need a constant source of lift, a constant source of updraft that goes into the parent thunderstorm. And this is what allows supercell thunderstorms to persist for long periods of time. If the environment is favorable for it, if all the ingredients are in place, as we talked about, moisture, lift, instability, and some kind of a trigger mechanism to get it going, then if you've got a good flanking line, a strong flanking line, you know, these cumuliform towers that rise into the parent thunderstorm, there's a pretty good chance that storm is going to have a potential to persist for several hours sometimes. And this is what we normally associate with some of the more prolific tornado-producing supercells, is a really robust flanking line, as you see in these two images. So what happens is those individual towers will replace the old updraft. You have an updraft that intensifies, it goes through its mature phase, probably associated with severe weather, sometimes tornadoes, sometimes not. Then that one is replaced by a new updraft, and you have a continuous feed of updraft for the thunderstorm. Okay, so the forward flank downdraft, we're kind of getting into some of the more obscure, slightly more challenging to understand concepts here. The forward flank downdraft occurs because you have a lot of precipitation with these supercell thunderstorms. Now, in a favorable environment for severe storms, we have the wind shear, right? So your precipitation will be displaced from your main updraft region. Okay, so in the picture on the upper left corner here, we have obviously a very nice updraft. You have striations there. You can see that it's probably rotating quite well. I think this severe storm actually did go on to produce a tornado. But you notice that all the precipitation is offset to the right there. Well, this view is probably looking from the west, it looks like. And so all the precipitation is falling on the north side of that updraft. And that's essential. You have to have precipitation falling away from the updraft. Otherwise, the updraft gets choked off and the storm dies. So the forward flank downdraft forms where all this precipitation is falling. You basically have this rain-cooled air that comes down toward the surface and kind of acts as a front, a lifting mechanism, and we'll get more into that in just a moment. So it's not that really scary-looking cloud base, okay? The forward flank downdraft is more of this rain-cooled air. Sometimes you have low cloud elements that develop with it, such as like a shelf cloud. But in most cases, if it's a classic supercell day, it's going to look more or less just like this, kind of a murky gray area where you've got a lot of heavy rain, probably some hail, and you may even obviously end up with tornadoes in the action area of the storm. So there's just kind of a quick view of where that outflow, or where the forward flank downdraft would be with the outflow winds. This is, I think, from the El Reno supercell from a couple years ago. So we'll move on. The rear flank downdraft, on the other hand, the forward flank downdraft, I should go back, is typically going to be rain-cooled. It's going to be pretty cold. The rear flank downdraft, on the other hand, in an optimal tornado environment, a lot of times is going to be warm. It's going to be hot, and it's going to be unstable air that's actually going to rise. So the rear flank downdraft, a lot of times, is associated with this thing called the clear slot. And what happens is the air is basically forced down because of pressure patterns in the vertical. And so as that air descends, it's compressed and it warms and basically evacuates all the cloud material in that region of the storm. So that's why you get a clear slot, kind of a horseshoe-shaped region where the updraft is. And there's a couple examples there. You see that the tornado in this case, there's not always tornadoes with every supercell, but in this case anyway, the tornado is on the north side of that clear slot, and that's going to be the case for pretty much all cyclic tornado or cyclonic tornadoes. It's not to say you can't have an anticyclonic tornado developing on the south side, but for the most part anyway, you're going to see tornadoes on the north side of that clear slot. There's another example on the right-hand side there. That's from the El Reno storm. Not as obvious of a clear slot, but there certainly is more sunshine coming in where you can see some cloud matter has evaporated. And of course you have that monstrous tornado to the north of that clear slot. So you can have a wet RFD, which is very common in high precipitation supercells, and of course you can have a dry RFD, which is what we see on the right-hand side and what we saw in the last image. Obviously, if you're a spotter, it's much more optimal to have a dry RFD, right? You want to be able to see, that action area, see if there's any tornadoes going on or any suspicious lowerings or anything like that. Problem is, sometimes, well, a lot of times, honestly, you get these high precipitation, wet RFDs, and your visibility drops to near zero. And that's a time when you need to start really paying attention to where you are with respect to the storm, what the wind is like. Is it at your back? Is it coming from the east or northeast? Because if it is, you're probably in trouble. You're in a bad spot. But this is not a time, if you're sitting in this location here on the left, in the left-hand picture, to say, well, I think I'll get a little closer and take a look, because this RFD probably is full of very large hail, incredibly strong winds, and if there is a tornado, you're not going to see it until it hits you. Okay, so that's a very important thing to mind when you're out spotting. Of course, there is kind of an in-between as well. Let's see if I can get that to come up. Kind of a hybrid RFD. This is kind of an almost wet RFD, but you can see the tornado there on the north side. Again, you have kind of a clear slot there where you've got some sunshine coming in, a lot of greenish color there, certainly probably a hail-producing storm and the tornado there. So again, the hybrid and the dry RFD is certainly much better for spotting. Okay, so how does the rear flank downdraft develop? Well, there's a lot of arrows and reds and greens and all that stuff on this image here, but the main thing we want to focus on is this purple arrow that comes off the left side of the image. It says mid-level winds. Okay, those enter the storm, they wrap around the mesocyclone, and because of pressure differences in the thunderstorm, you actually end up with relatively high pressure kind of in the mid-levels, and where your tornado and wall cloud are, that's where the pressure is extremely low. So that air then descends and compresses and warms as it does so. Okay, and it's thought that the RFD is actually one of the most instrumental or most critical parts of tornado genesis, because you're forcing this very unstable, very warm air down to the surface, and then it immediately is wrapped back up into the circulation to intensify and stretch the vorticity associated with the low-level circulation. So again, just to kind of reiterate this is the El Reno supercell again. Let's just assume we have mid-level air entering the storm in this location, strong mid-level inflow there with the updraft. That then descends because of those pressure differences in the vertical. And of course, you end up with this very warm, very unstable air hitting the ground. Now, there are instances where you have a cold RFD, and usually when you end up with a cold RFD, your tornado potential is not quite as high. That's not to say it's zero, but you really need a warm, unstable RFD to stretch that vorticity in the low levels of the thunderstorm, especially if you're looking at strong to violent tornado potential. Okay, so we're getting back to more of the structure elements here. The mesocyclone, I think we kind of already touched on this. That nice striated updraft base, it's basically just a rotating updraft. Sometimes you can see it clearly, as you can see in pretty much all these photos. Other times it's not quite as easy to make out, especially in cases where the cloud bases are really high. You don't have a whole lot of moisture in the air necessarily, but you can still get rotating thunderstorms. Sometimes it's really hard to make out whether you have a real well-pronounced mesocyclone or not. But certainly the mesocyclone can provide some of the most photogenic aspects of supercells. So how do mesocyclones form? Well, we talked about environmental wind shear, right? And then we're going to go kind of a 1, 2, 3 here. And something that you might notice here is that we've got circulation in the wrong direction. Don't worry about that. The fact is the environment is basically favorable for this horizontal rotation in the atmosphere, right? Well, an updraft comes and tilts that rotation into the vertical, and so the updraft then starts to rotate. And finally, you can get intensification when that updraft strengthens, and you can end up with much stronger rotation. So this is a very basic, obviously, overview, but basically when you start stretching that, when your updraft gets more and more intense, you're able to make that mesocyclone spin faster and faster. And usually that's going to obviously start in the mid-levels of the storm first, and if conditions are favorable, then it'll eventually lower itself toward the ground. So here's kind of a not-so-basic overview of mesocyclones. And I'm going to do something here real quick. There we go. All right. So again, this little image on the right-hand side of the screen denotes that that wind shear in the environment, which is causing these tubes of horizontally rotating air above the ground. Okay. Again, this is just a schematic, a very basic overview of how this works. But this is getting into a little bit more of the role of the forward flank downdraft and the rear flank downdraft in reinforcing and intensifying that mesocyclone. So the forward flank downdraft we'll start with. Remember we talked about that's a fairly cool, stable air that's falling from the precipitation region of the thunderstorm. Well, it kind of acts as a front effectively. And you have these lines of horizontal rotation, horizontal spin, as you can see on the right-hand side, that are basically fall out from that environmental wind shear again. Those vortex lines are pulled up and into the mesocyclone into the low and mid-levels of the storm. So that continues to support that rotation and continues to promote the mesocyclone's longevity. The rear flank downdraft obviously comes around. You have that warm, unstable, descending air that comes down toward the surface, and as that re-enters the thunderstorm near the base, you have a very tight circulation down there, so that actually acts to intensify the mesocyclone, and ultimately, if you have a wall cloud, can lead to tornadogenesis. So just kind of a basic lesson here. You've got, say, a weakly rotating mesocyclone here. You have a persistently rotating storm. You've got the flanking line. You've got plenty of instability. The storm continues to grow. Mid-level mesocyclone has persisted for a while. What about the RFD? It comes in and the updraft intensifies because you have maybe a new updraft entering from the flanking line. So you actually end up stretching that mesocyclone and can actually intensify it both in the mid-levels and certainly near the ground where we expect tornadogenesis to happen. Okay, so here we're going to just talk about some of the other features that obviously kind of fall out of supercell thunderstorms. Wall cloud is, of course, one of the obvious ones. Here we have a few examples. A lot of times you'll notice the wall cloud points down toward the rain. Again, remember that forward flank downdraft, that's rain-cooled air. If you see the wall cloud kind of pointing down toward that rainfall region, you know it has a source of moisture. And a lot of times that helps the wall cloud descend closer to the ground because you get a lot more evaporation, or not evaporation, but condensation rather near the ground if you have a lot of warm, moist inflow. So how does the wall cloud form? Well, again, you've got the forward flank downdraft region. You've got very, very warm, moist inflow on the most optimal days. That cool air descends along the forward flank downdraft region, and you end up with sometimes a tail cloud with that wall cloud, although sometimes they're pronounced, sometimes they're not. You shouldn't be looking for a tail cloud all the time to think there could be a wall cloud or a tornado. But sometimes in optimal situations, you do end up with this kind of ground scouring cloud formation that then rises up into the updraft base, where if you have a mesocyclone, it can begin to rotate. The tornado itself, obviously, it doesn't really need any introduction, and of course it's probably why a lot of you are registered for this webinar. You're probably very interested in the formation of tornadoes and the environment that it takes to support tornado formation. And you know, the truth about it is that even here in Oklahoma, even in Kansas, the Great Plains, on average, in general, tornadoes are relatively rare. You have to have a very specific set of ingredients to allow thunderstorms to promote tornado potential. And even if you have all the ingredients, sometimes you don't get a storm. Sometimes the cap's too strong. Sometimes the upper level wave comes in too late or too early. There's so many different factors that can go into this. And while we do on average get quite a few tornadoes in the plains, they're still relatively rare, and there are people that live in the southern plains their whole lives and never see one. So let's talk about tornado formation. Okay, well, we already know we've got strong inflow, right? Now, sometimes preceding tornado genesis, you get very strong reinforcement of inflow, particularly if you're east and east-southeast of the circulation, and that should be a signal to you if you're dealing with a tornadic storm that your tornado genesis may be imminent. You may be dealing with a tornado very shortly, and if you're too close, that's time to make sure you have an escape route and get out of there. So again, here we're re-emphasizing our forward flank downdraft, our rear flank downdraft. Those two are very important. Remember, the forward flank downdraft, in honesty, in this picture is probably a little far off to the right. It's farther off to the right because we're looking at the wall cloud here. But the idea is, of course, that you have rain-cooled air that's allowing for this condensation near the lower part of the cloud base. So you're getting a lowering of the cloud base. The cloud base is already spinning. Not all tornadoes are going to look like this. Obviously, this is a very classic-looking tornado. And, of course, we have our rear flank downdraft. That air, it's descending from the mid-levels of the storm, hitting the ground, fanning out, and going basically directly back into the low-level circulation. So right at the ground or near the ground, you have this extremely low pressure area that develops that's associated with that tornado. And that rear flank downdraft air rises right there to reinforce that tornado genetic process, as it's, of course, still unstable, at least in the optimal conditions. Now, I should mention this is still a very poorly understood process. Not all tornadoes form the same way. This is like the classic model for supercell tornadoes. So it's an important thing that if you're out storm spotting, don't just rely on the fact that, oh, well, you know, there's a forward flank downdraft and I've got an RFD, but there's no clear slot. Well, there's not going to be a tornado. Well, no, that's not necessarily the case. Tornadoes can form many different ways. They can form not even necessarily with supercells. They can form in pulse storms out on the high plains, and we'll talk about that in a minute. But this is basically the most commonly accepted model, and I tried my best not to botch the explanation, so hopefully that worked out all right. Okay, so what about multiple vortex tornadoes? So we know that multiple vortex tornadoes tend to be associated with the most significant damage, tend to be the strong to violent type tornadoes. Well, remember how we talked about the RFD originates in the mid-levels of the storm, but because of pressure differences, it descends toward the ground. Well, we're not talking about a downdraft here necessarily, but you basically end up with the same effect within the tornado itself. You have that extremely low pressure at the ground, and at the base of the cloud, the base of the wall cloud, the top of the tornado, whatever you want to call it, the pressure is relatively higher. And we have to remember that air tends to flow from high pressure to low pressure. So you end up with this downward force toward that low pressure near the ground. And you'll actually see this sometimes. There are videos of this where you have a very tight single vortex tornado at the ground, and up just off the ground you can see it start to widen. And eventually that flow will reach the ground and spread out, and your tornado will widen to the point where you get what's called vortex breakdown. Now, the reason that vortex breakdown occurs has to do a lot with frictional imbalances near the ground. But basically, you end up with these, the general area of low pressure near the ground, but then breaks out into these smaller areas of low pressure that are circulating around that larger area. So what can happen is you have all that energy in one vortex. Now you're going to break it into these very small, very concentrated areas of vorticity. And if you believe in conservation of momentum, then those have to be spinning a lot faster than that larger vortex had to be spinning. So when you have multi-vortex tornadoes, you can be pretty darn sure that the winds inside those suction vortices are going to be much, much stronger than they would have been had it been a single vortex. So here's just a few pretty pictures of multiple vortex tornadoes. Some of them were pretty catastrophic, resulted in loss of life. So they're certainly something you don't want to mess around with. They tend to be a lot more common when you have low cloud bases and you have obviously very favorable tornado parameters in place. Okay, so we've kind of talked about the traditional supercellular tornado, and we're going to get into some less traditional tornado formation processes. The first one is called a land spout. These are generally non-supercell tornadoes, although sometimes if you have weak supercell structures, they can still result in land spouts. Basically what happens is you have some kind of a boundary where you have some environmental convergence and maybe some weak spin in the vertical along that boundary. And a thunderstorm develops right on top of that. Well, what happens when we stretch vorticity? We already talked about this. It intensifies. So you can actually end up with a basic summertime thunderstorm with a strong updraft stretching that vorticity on that frontal boundary, and it can result in a tornado. And a lot of them look like this, kind of a ropey, dusty, get this small funnel. Sometimes there isn't even a funnel, honestly, but it's kind of this dusty, snaky looking thing. And these tend to be a lot more common in the high plains, out near Denver and even into Wyoming, New Mexico. It's not that they don't happen here. They have happened, but they tend to be more common out there where you tend to have those higher cloud bases. And it is important to note, just because it's not a supercell tornado doesn't mean that it can't produce damage. I want to say at least a handful of these landspouts have produced EF2 and EF3 damage at times. What about other things that spin that aren't tornadoes? Well, one that's very common, especially with outflow dominant storms where you have a lot of cool air coming out, are gustnadoes. And they basically, you got this front coming out, this outflow, rain cool air, but you still have a pretty strong updraft going into that thunderstorm base. And so you end up with these small circulations on the leading edge of the outflow that are then stretched into the updraft. Now, these usually don't cause a lot of damage, although they can cause some minor tree damage, maybe some outbuilding damage if they're weakly or not anchored. But in most cases, these are just really dusty and they look kind of scary, especially when you start looking at the shelf clouds that can look very, very ominous. Okay, so we talked about supercell tornado processes, and we've now touched on non-supercell processes. And I think now is a good time to delve into a special case. Now, this is from March 25th of this year. Many of you probably remember this as the day that the tornado struck Sand Springs, Oklahoma, and then of course there was also a tornado that touched down in Moore. Now, this was not your typical tornado formation process. We're going to look at it in detail here. But before we get into exactly what happened, it's important to remember that in frontal boundaries you have environmental vorticity enhancement. And in this diagram you can see it probably would be northwest or west winds on the back side of the front with southeast winds on the front, ahead of the front. So you end up with this weak cyclonic spin right at the boundary, okay? Just remember that. Keep that in mind. And the other concept you need to remember is the stretching of vorticity. That causes a much stronger vortex, okay? So you end up with kind of this weak rotating column of air. Supply that with some kind of updraft, then it's going to rotate much more rapidly. That's like what we saw with the landspouts, okay? So let's step through time here. At about 6:07, we have supercells out in, well, central Oklahoma, northern and central Oklahoma, kind of back behind a frontal boundary. These are storms that have strong mid-level mesocyclones that are producing hail and high winds, but at the time the tornado potential appeared to be quite low. Now we've got the front here delineated in the dashed blue line, okay? So we go through time here, and we start to notice that you get a little bit of a kink in the frontal boundary here. Now, I know you can't really make it out, but there are weak echoes along that leading edge. It's a rough estimate of where the front was, but it's fairly close. So we're looking at this storm particularly over El Reno, Yukon, Mustang area. And we can see high reflectivity there. If we were to look at velocity, especially aloft, you would see some rotation with that. Again, very large hail have been reported with this storm. I think golf ball to tennis ball sized hail, and some pretty strong winds as well. If we go through time, 6:33 p.m., we start to see the kink in that front approach that thunderstorm. So we have a supercell here, okay? Don't get me wrong in that, because this is a supercell. But we don't have the low-level rotation that we would expect to see with a tornadic storm. But the cause for concern is that this front is approaching the updraft, okay? So let's go on into time, 6:41 p.m. Now we have a pretty well-pronounced kink in the line. And this, of course, is just west of, this is actually, as the storm is entering Moore, just north of Norman, just south of Oklahoma City. And let's zoom in on that. Okay, so you can see that front that's pulled basically right under that updraft. Let's zoom in on that again. Okay, at 6:41 we have basically what we would consider a small little reflectivity ball, or I think it was even a debris ball at this time. So, it was evident that what happened was this front approached the base of the thunderstorm and rapidly developed this tornado. And this developed from the ground up. This did not develop in a typical supercell process. This was not a rear flank downdraft that descended. This was not streamwise vorticity enhanced by the forward flank downdraft that then led to a wall cloud or anything like that. This was a tornado that developed on that frontal boundary and then was pulled into the thunderstorm. So there's the view without all the highlighting there. So you can see pretty well pronounced curl there that develops just south of Moore. So here's a picture. This is from Chris Karstens. He's a partner that works with us here in the National Weather Center. Good guy, and he was looking north from Norman actually at the time, and well, we got what almost looks like a shelf cloud here, honestly, in the cloud base. You see maybe some striated elements there, but he did note there was a funnel cloud. Well, one of the fundamental things that we talk about in storm spotter training is you can't see the ground in this picture, so there's no way you can tell that's a tornado for sure, unless you have some other source of information. And if perhaps you could go out into a field and take a look, you might see some dust or something like that, but at this time he had no way to know. Well, I myself saw this feature when I was driving home as well, and to me it looked like a funnel cloud, but there was no way to discern whether or not that was actually reaching the ground or not. Well, of course, we found out that it did reach the ground, but it basically started at the ground where that frontal boundary was. We had that weak ambient vorticity in the atmosphere, and that strong mid-level mesocyclone and extremely strong updraft resulted in that rapid tornado formation, but it started at the ground and moved up from there, okay? So very, very complex tornado formation process. So here's the final path of that tornado, and you can see that light green shading there, that's pretty much all wind damage. But where that narrow path is, the light blues, the darker greens, and even the yellow, a couple little yellow spots there, that's where the tornado path was. And actually did last for quite a while, went through Moore and then even approached parts of northern Norman. I think it started in southwest Oklahoma City. So what is the moral of the story here? Why do we even talk about this? Well, it's important to note that not all tornadoes fit neatly inside the tornado genesis conceptual model that I explained earlier, okay? That was a supercell process. That's what we tend to look for on days that are very favorable for tornadoes, especially long track violent tornadoes. The day that we just talked about was certainly had some potential for tornadoes. There's no doubt about that. It was not a 0% chance. But the conditions and the environment in general weren't all that supportive of tornadoes. So it's important to note that when you're out spotting, just because the conditions don't look all that favorable for tornadoes, maybe the significant tornado parameter isn't 3 or 4 or 5, it doesn't mean there can't be a tornado. And in some cases, you end up with these mesoscale or very localized tornado events that form because there's a boundary there or there's some kind of a storm interaction, storm merger. So that's why we wanted to cover that. So to sum it up, you've got that strong mid-level mesocyclone, extremely strong updraft associated with the supercell coming into southern Oklahoma City in the presence of that front, or very close to that front, which kinked back up under the updraft. And then we had the vortex stretching from the ground up. So we ended up with that tornado formation near the ground. If you saw the video of this tornado, I think you can attest to that. It's a lot of debris near the ground, but you don't have much of a circulation aloft. And that's what resulted in that tornado. So we had both supercellular processes, because we had a supercell, and we had non-supercellular processes. So again, a very complicated scenario indeed. All right, so that pretty much sums up the storm structure, the case study, all that good stuff. I'm sorry you had to bear with me for so long. But Vivek is now going to come and, I think, conclude with some safe positioning tips and also some resources for reporting severe weather to us.
All right, thank you, Mark. And here we go. Here's a typical schematic of a supercell. And in this particular diagram, you can see the safest position for when viewing a supercell storm is actually usually toward the southeast. And again, this will vary depending on the motion. For example, if you are southeast of the storm and the storm makes a hard turn to the right, you may become in danger and may have to, drive south out of the way. But the good part is being southeast is you won't have to drive through the hail. If you were located a little bit farther to the north, you may have to drive through the hail to escape the storm. In this particular example, the storm is moving toward the northeast, so if you are southeast of the tornado, you will be in a good spot, and you won't have to worry about being pelted by hail or heavy rainfall, which could obscure your visibility. The key part is always to be in a position where you can see the action area or the area where you're expecting the tornado to develop. Here's an example. In this particular example, we have chasers positions marked here. And these chasers here are in a somewhat dangerous spot because they are located in the heavy precipitation. The storm is either moving to the east, or if it starts turning to the southeast, they may get hit by very large hail, and it'll make it very difficult for them to escape if a tornado does develop. These people are also in a somewhat dangerous spot, again, because they're sort of north of where you'd expect the tornado to develop, and they can't really see what's going on because they have this heavy precipitation blocking their view to the south. So again, both these people over here and these people over here have trouble sort of seeing this action area where the tornado may develop. However, these people right here, they're away from the heavy precipitation, and they can easily see if a tornado is developing toward their north or northwest. And they also have an easy escape route if the storm makes a hard turn to the right. Now, supercells often can split, and you have a left split and a right split. And it's something to consider while chasing these storms, because if a storm starts splitting, you may be in trouble. Because if you are, say, north of a storm and it starts splitting, you may get hit by the left split, which is more likely to produce very large hail. They do rarely produce tornadoes, but they can sometimes do so. And then you have the right split, which is more likely to produce tornadoes, and this can also contain very large hail. So it's also important to be situationally aware. If you start seeing two updrafts, a second updraft, the storm might be starting to split. And splitting storms do present a challenge. Again, left movers are notorious for massive hail. Right movers may turn southeast or even south-southeast. So you must be positioned safely. If you're in this area here, you are not in a good spot in the yellow X because you're going to be getting large hail. If you're in this pink X, you're also not in a very good spot because this left split is going to continue moving more due north or move more toward the left compared to the mean motion, and you could get some very large hail. If you're in the red X, right now you're in a safe position, but you must always stay situationally aware because if that storm turns more to the right, and when I mean turn to the right, I mean compared to the mean motion. For example, in this case, if the mean motion is toward the northeast, a left-moving storm will be moving due north, and a right-moving storm might be moving east or east-southeast. So again, this pink X, you need to get ready for some large hail. This yellow X, hail, wind, and zero visibility. So if this storm starts to turn maybe over to the left and there's a tornado there, you could be in trouble. And again, the red X, safe until the storm takes a hard right turn. You always need to be situationally aware. When making a report, it's always good to give us as much information as you can. Please tell us who you are, where you are, and when we mean where you are, not just where you are, but where the tornado is. Hopefully you're not centered right where the tornado is. So, for example, if you see a tornado, tell us where you are and then estimate how far away that feature is. Is it to your northwest 4 miles, for example? What do you see? Where did you see it? And when did it happen? And if you want to make reports, an excellent way to do so is on our website. Right on the front page, you can submit a storm report, and this directly goes to the forecasters that are issuing the warnings. So it's a great way to get a report to us. You can also download this app for your phone that NSSL created. This is available for iPhones and Android, and you can, for example, report large hail using this particular app. You can also sign up for Spotter Network. Using Spotter Network, you can again make reports, and these reports again go directly to the forecasters at the National Weather Service. So it's another great way. And the nice thing about Spotter Network, it also gives us your location as well and the time that you reported it. So it is a great way to give us reports as well. And here's an example of a Spotter Network report. Again, the nice part about it is it gives us the location, the time, and it's plotted a lot of times on GIS. If you have a GIS application, you can even view GIS radar application, you can even view the reports. Another way to report to us is using amateur radio. We are WX50UN on the amateur radio. You can also send us reports by email. Now the email reports, a lot of times we don't get real time, but after the fact, if you have damage, for example, or pictures or anything from a storm event, we'd love to see them. So definitely email us any reports after the fact. Now these reports we won't usually see real time, but it is great for after the fact reports.
Can you go back a couple slides for the spotter network? Keep going. Right there. I've got the same thing up. You had a lot of questions. You can tell me you had some questions about this thing for MPing.
Okay. All right. We had a lot of questions, I guess, about MPing. So again, here's the link for MPing.
You can also just remind them too that we'll be giving the presentations. They can look at it.
Yeah, and again, these presentations will be emailed to you, but I guess we are getting a lot of questions about MPing. So here's the link. If you want to download the app, again, you can either look at it at the Google Play Store or the iOS Apple Store, and you should be able to just search for MPing, and you should be able to make reports, and it's a great way to do so. And remember, the most important part is safety first. No report, data, video, or image is worth your life. So safety is always first. If you can't make a report safely, do not make the report. Safety is always first, and that's the most important part for storm spotting is safety. There are many ways to keep in touch with us. I know many people are outside of our warning area, so your local National Weather Service office will also have a Twitter or Facebook or website as well. But if you are within the Norman County area, so the western two-thirds of Oklahoma or western North Texas, here are ways to keep in touch with us. Again, we have Twitter, Facebook, and when we have high-impact weather, a lot of times we do make YouTube weather briefings. And always our website, it has the most up-to-date information, including graphics that we often post and update frequently during weather. And with that, that is the end of the training. But if you want more information, you can check out Rich Thompson's. He's a Storm Prediction Center lead forecaster. If you go to this website, you can learn a lot more of the science behind tornado forecasting. So I recommend you to do so. All those are video archived, and you can look at PowerPoint presentations that Rich Thompson created. This is a great way if you want to go even more in depth from what we showed in this presentation. And with that, that is the end of the presentation. We'll take questions for a few minutes. Otherwise, thank you for joining us, and have a good evening or good afternoon wherever the world you are located. And just a reminder, certificates and a link to the slides will both be emailed within the next few days to next week or so. It may take a little bit because we have some active weather this upcoming week, but we'll get you that as soon as possible. Again, certificates, and the certificates will be blank, so if you have several people there, you can make sure to, you can print out several copies and write each individual's name on there. All that will be emailed hopefully within the next week or so. So again, if you want the slides and you need your certificate, don't worry, it'll be coming, not tonight, but down the road. All right, okay, have a good evening.